We are live. Hello, hello. We are live. हेलो। खांसने की आवाज तो आ रही है तेरी उसमें। तो ठीक है। All right. So, just for the audience, we can show them the final website now. So this is the final website. अब तेरे को मेरी स्क्रीन दिख रही है?
नहीं, इस पे तो नहीं दिख रही है। उस पे तो करिएगा ना।
रुक जा, वीडियो निंजा पे कर रहा हूँ मैं, रुक।
इस पे तो दिख रही है।
स्ट्रीम में ना इस पे कर देता हूँ, वीडियो निंजा पे लाइव दिखेगी तेरे को। All right, just for the audience, this is our current website. This is basically what we are trying to achieve. This is the current pipeline. This is what this is what our vision is for the dashboard and the infrastructure, ongoing efforts and pillars. Looks really nice. We are trying to answer these questions as we go about it and build the startup. Retraining on. Eval specificity. This is the main business crux over here. This is the direction we are going in right now. We're gonna try to run this Cosmos experiment soon to come up with our taxonomy. This is the vision right now. And this is a little bit about us and about our company. This is the main goal. All right, that was enough about the website. We can close that website now and start actually working on our thing. Okay, तो एक्सकैलेटर खोलना है तेरे को?
मैं क्यों खोलूं? तू खोल ले। तू खोल ले, क्या लोड है उसमें?
ओके,
तेरे
तो अपन
वहीं के अंदर
पाइपलाइन,
है।
हाँ मैं इसमें एक नया इसमें खोल लेता हूँ. Your instinct is exactly right here. Cosmos reason is the perception and reasoning engine. It watches failure clip and tells you what physically happened, but it cannot tell you what category of failure that is, how severe it is relative to your deployment KPIs, or what coverage gap it implies. The classification prioritization. Okay, that is our first part.
Mm-hmm.
Okay, and then it watches a failure clip and tells you what physically happened, but it cannot tell you what category of failure it was. What coverage gap it implies. That classification and prioritization logic in is instructs taxonomy sitting on top. Cosmos reason is the eyes, taxonomy is the judgment. ये पढ़ भाई.
Mm.
तेरी भी स्क्रीन शेयर कर ले यार और तू ये टेक्निकल डेटा खोल ले अपने उसमें.
Technical data?
जैसे ये कॉस्मो रीजन की गिटहब.
अच्छा, हाँ, रुक जा।
कॉस्मो रीजन. ओके, ये रहा इसका डॉक्यूमेंटेशन थोड़ा तो.
Mm-mm.
मॉडल स्टार्टिंग ऑप्शन. ये तो अपन ने पढ़ लिया था.
Yeah,
कॉस्मोस.
but yeah, okay, this is what you're talking about. Cause reason to.
अरे यार, ये स्क्रीन शेयर का कुछ करना पड़ेगा भाई तेरे. ये वीडियो निंजा पे पूरी क्वालिटी कुछ भी नहीं आती सही.
Hmm.
तेरी स्क्रीन में डाल ही नहीं सकता है इधर. बट तेरे को मेरी सही दिखती है क्लैरिटी.
हम्म।
ये ऐसा क्यों हो रहा है भाई? एक सेकंड, ऐसा तो नहीं कि मैं कर रहा हूँ इसलिए तेरी खराब आती क्वालिटी?
हाँ अब देख, अब अच्छी दिख रही है। हाँ अब अच्छी दिख रही है।
नहीं, मेरे को तो वैसी दिख रही है। रुक एक सेकंड।
अबे तूने तेरी क्वालिटी डाउनग्रेड तो नहीं करके रखी है? स्ट्रीम पे तो सही दिखता है।
ओ वेट, अरे हुई तो सही। सही तो हो गई थी एक सेकंड के लिए। बढ़िया बढ़िया। कॉस्मोस प्रोडक्ट, कॉस्मोस ट्रांसफर मल्टी कंट्रोल मॉडल फॉर सिमुलेशन टू फोटो। ओके ब्रो, आई नो, आई थिंक आई नो हमारा पहला एक्सपेरिमेंट क्या होने वाला है अब।
ओके।
डू यू सी दिस?
यस कर रहा है। हम्म। What is it? Where is it? But I can only see my screen.
रुक जा, बता रहा हूँ। Yeah,
Mm-hmm.
this is Cosmo reason.
Okay. Yeah, this is
Mm,
what I'm looking at. Right?
yeah. So we'll basically run this model on. This is going to classify the failures.
Hmm.
What's Cosmos transfer? This is Cosmos predict.
Hmm.
Data processing and evaluation, speed of efficient data processing and evaluation. Cosmos curator.
Hmm. Okay, so in this it says that the inputs, the control modalities for the model,
Hmm.
right? That
RMP4.
it yeah, that it takes are like noise in the video, depth in the video, edge in the video, segmentation in the video, blur in the video, and the spatial temporal control weight video as well. We have
Mm-hmm.
like a diffusion backbone, and I think these are critical variables that we take in, and then we feed it into the spatio temporal control. Right, so we have a function that preserves the original structure, and then this is best for Changing textures, clothing, or lighting where the underlying shape must be maintained. Okay. Hmm. Let's see.
Hmm. Why are you looking at this?
I'm looking at this the experiment that they have performed with the agriculture images and how they have used Cosmos, reason, and modality for training the whole thing.
I'm gonna put your.
Mm, because
Mm,
this is something that we are trying to do.
mm-hmm. I cannot see anything, whatever you're sharing, because it's very blur.
Hmm. Okay.
Wait, I'll come back.
I think everyone should try this. Mio.
What is that?
This is some natural flavor water shit. If you don't like
Hmm.
your water plain, you can add some flavoring to it.
Mm,
Like it has a bit of vitamin, sorry, sodium. That's it. Electrolytes. That's all.
that's what I'm drinking right now.
Dude, we have to do something about this screen, right? The screen.
Yeah, please look
But
for some
this
alternative.
some alternative. You know what we can do?
Yeah,
Can you do me FaceTime?
yeah, one sec.
Yeah.
FaceTime for what? What are you gonna do on FaceTime? Passion in the. Oh. Yeah, you're on mute.
FaceTime कर ले भाई.
क्या हुआ उससे?
नहीं करेगा नहीं FaceTime. क्या होगा 4 बार ये पूछेगा जिससे.
कर रहा हूँ, रुक, इस पे से बंद करना है।
तो कह रहा था सही भाई.
अच्छा,
करना नहीं
रुक।
है, रंडीबाजी ज्यादा करनी है.
ओके, वेट, वेट। हम्म। हम्म। बस यहाँ की और ये वो कर दूंगा म्यूट और वो, ताकि दो दो बार आवाज ना आए, है ना?
हम्म,
Okay, this is much clearer. I'll put this. Hmm. Yeah, you can start talking about it now. What are we looking at?
we are looking at wait, where is it? So yes. So what we are looking at? We are looking at robotics domain adaptation library.
Mm-hmm.
This like showcases how like this is more for cosmos transfer
Mm-hmm.
robotics application. Earlier we were like, taking a look at this. This was most interesting part. Like this was the generate photorealistic agriculture images for robot perception training. So
Mm-hmm.
in this experiment, what they have done is they have used eight A100 GPUs and Cosmos transfer model. And the other thing they have used is a depth estimation pipeline that is for measuring the depth of their
Mm-hmm.
crops. So they have used
Can you open Notebook LM on your new tab
wait,
and add this link over there so that we can study about this?
dude, like what are you gonna study? Just go through this documentation.
Okay, okay.
Yeah, like it's more elaborate. It's more than enough to understand what they have done. Like we do not need to
Okay,
ask too much
scroll
about
up,
it.
scroll on
Yeah,
top, scroll on top. Post training plus inference. So, what is the objective of this? Like, what are they using this Cosmos Transfer 2.5 to do?
generate
G-
for generating photorealistic agriculture images.
Okay.
Dude, it says at the top.
Yeah, yeah, shut
What
the
the fuck?
fuck. Osman Khan, okay, whatever. Scroll down. Training robust perception models for agriculture robotics requires diverse, high quality labeled data spanning crops, growth stages, weather conditions, and disease states. Okay, recipe. Wait. Only 1% real data and the remainder generated synthetically using this pipeline. Cosmos transfer is well suited to this domain because it enforces spatiotemporal structure, allowing visual variation while preserving the spatial relationships critical for centimeter level precision agriculture. Post training bridges the domain gap between the foundation model's visuals prior and the appearance of row crop fields. Even a modest training run yields strong results on in distribution crops and promising generalization to unseen ones. What does that word mean? Spatiotemporal structure.
Spatiotemporal structure is this thing like the way this thing is observed over the image, like like a leaf has a structure kind of a thing, right? Like
Hmm.
when you map it over the ground, like the way we are looking at right now, right? So
Can you
this
copy that
that
text and put it in some AI to explain it?
eh,
The last no, yeah, the last line over here. This
the last
Cosmos, yeah, the last paragraph. Cosmos transfer is well suited. Yeah, this one. Just copy this and we need to understand this.
explain the about to
If you have a super smart robot that learned by looking at tons of pictures from all over the world, now you want it to help on a farm, man, crow. Wait, wait, wait. Array, bro, wait. Let me read.
Read na?
Array, scroll up. Yeah. Cosmos transfer is like giving the robot special rule book so it understands space and time, where things are and how they relate to each other. This helps the robot notice differences like plants looking a bit different but still keep track of where everything is in the field, like rows, spacing, etc., which is super important for farming. The robot already knows a lot from general pictures, but farms look different, so we do little extra training called post training, kind of like giving it practice on farm pictures. After just a bit of this practice, it gets really good at recognizing crops it has seen before. And it even does a pretty good job when new crops it hasn't seen yet. Simple analogy. Scroll down. It's like teaching a kid who's good at puzzles. First, they learn puzzles in general, then you give them few farm themed puzzles. Now they can solve farm puzzles really well and even figure out new ones. Okay. Okay, go back to the doc. Can you scroll a little bit up? What was written over there? Follow the setup guide for general environment setup instruction, including installing dependencies. Okay, hardware is 8 A100 GPUs. Cosmos Transfer 2.5 model weights and training framework. Depth estimation pipeline synchronized RGBD from fleet cameras or an off-the-shelf monocular depth model such as Depth Anything V2. What is this? Depth estimation pipeline.
Yeah, dude, I told you, right? We are looking at the photo
Mm-hmm.
from an angle, right?
Yeah.
So the robot needs to know what angle it, are we it on. So we have to measure the depth of the whole camera angle, like the geometry, like as we have as it is said over here, right? Root over here. Where is it? Or is giving like a rule book so it understands space and time, right? For us to understand the space and time, we need to give the depth of the space and the time that we are looking at. So the space over here is the depth that we are looking at. So we
Mm-hmm.
need to make sure that what depth are we looking at. So right now, this is how it looks at from, this is the 3D render and this is the base. Like if you look at in a 2D way, you see that there are plans over here.
Mm-hmm.
So that is where depth comes in. It
Uh,
acts as a third dimensional vector for our cosmos model to understand how the leaves or the plants exist in that geometry. So they are spread across so when the robot looks at it, it looks in two dimensions that okay,
mm-hmm.
there are there are some patterns that exist. But how depth what is the depth of those patterns? How big are those patterns? To find out
Mm-hmm.
that we need to use a third dimensional vector that we call it as the depth. So with the
Mm-hmm.
help of that, our our model is able to learn and predict much better with zero shot evaluation. That is what that they are trying to say it over here. So the base Cosmos Transfer 2.0 checkpoint does not
Okay.
perform well on agriculture data. So the base one doesn't perform that well.
Okay. And what was the diagram above that? Yeah, this agriculture domain gap. Foundational model prior, generic scenes, controlled lighting, common objects, limited seasons, agriculture reality, row crop fields, variable sunlight, leaf morphology, disease symptoms. Okay. Can you scroll a little bit more up? Okay, no, down, down. Agriculture robotics operates in blah 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 blah. Okay, yeah, this is the main thing we are building on. Can you scroll a little bit up? What was the, yeah, what is this? Property, value, clips 3000, duration 10-second per clip, training resolution, train. Okay, okay, scroll down. Okay, so do you think it will make a difference if the quality of videos are different? Like, um, let's say these videos are shot on some camera that was like just like a normal camera, but if for the same thing we use like really good high resolution cameras to capture that 1% data that they are talking about, and
But you
then
still need the third dimension depth.
yeah, I'm not saying we'll still need the depth part, but what I'm trying to see is changing the environment, like changing the resolution of the video, like getting a more high quality video, gonna affect the generation of the synthetic data that it will, you know. Okay, scroll down. Let's read it completely first.
Hmm. I
What
think
does that mean? What does that mean? Like scroll up, scroll up, scroll up, scroll up. This table above this diagram. What does this mean?
this is like this the
Property,
data preparation, like what the data they are preparing. This is
crops,
the original
depth.
original resolution and then the
Hmm.
training resolution.
And how are they getting the depth? Like, how are they measuring the depth?
This it says over here, right? This uses synchronous depth.
Synchronized depth from fleet cameras, but monocular depth estimation can substitute when hardware depth is unavailable. What does that mean? Can you copy this in ChatGPT and yeah, the whole thing, the whole thing. Bright white, far away, dark black, close. So instead of colors, it shows distance. What's happening in your code? We use smart AI tool. Go scroll down. Estimator. This is like turning on robot's brain that can guess distance from a single picture, even if you only have one camera. You got a picture, you show the robot a photo, and it tries to figure out what's close, what's far. Okay, scroll down. Oh, got it. Basically, it captures the image and then it converts it into black and white. And the more black it is, the more close it is, and the more white it is, the more far it is. And the scale is between 0 and 255. I think that's what it means.
Hmm.
Yeah, yeah. See in the bottom.
It says over here as well.
Uh huh. Yeah. Well, wait, what is this table? Sample ID, video path, depth path. All of this is string type.
Hmm.
Required, yes, 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 recommended. So where are we feeding this data again?
To the model.
Dataset schema. This is the dataset schema we are going to use, right?
Yeah.
And this is the input that's going to go in the model.
Yeah.
Okay. Take screenshot if you're trying to copy it.
No, no. I'm just going through. I'm not copying that. It's gonna be over here. I will
Uh,
let Lord God take care of this. Anthropic. Need more credits.
okay,
Need
scroll
more
down.
tokens. So I think this is what we did earlier, but we did not had this dimensional video vector videos.
We just had the RoboFact dataset, right?
Yeah, like we did only two-dimensional videos and tried to see what our vision language model does it without the physics simulation.
Mm-hmm.
Right now we have this per clip depth video that gives us uh, a way to simulate our Cosmos models
Mm-hmm.
to understand how or what the image is talking about. So this is the most important thing. We have latent frames. So latent frames, what so latent frames is like before latent frames, we need to know what is a latent function and how does it work. So we will ask ChatGPT again, explain latent functions.
But okay.
Because latent functions and latent frames are similar kind of things, but
Mm-hmm.
both of them serve the same concept.
All right.
Okay, so see, latent means first of all that is hidden inside the model. Instead of directly working directly with the raw images, which are big and messy, the model compresses them into smaller and smaller representation, like a secret code. Now we can use
Oh,
that
it's
latent.
like a hash function.
Yeah, but but now that latent function can be converted into a frame, right? So we say a compressed version of an image, right? But in one video frame. But in AI language, it's not a normal picture. We can look at different shapes, positions, or patterns. So when we take a look at a picture, the picture or a video or a frame, it is getting pixelated into smaller dimensions, and at that point, AI can look at okay, what happens if I remove this data? What are the things that I can see? So AI can do a lot of things like that. Then a latent function is what the model does inside the hidden space. So whatever the frame or whatever is happening, right,
Mm-hmm.
that is gonna be hidden. It's called a black box situation right now. That let's say whatever the videos or something that or any prediction that our model will be doing,
Mm-hmm.
that that is not deterministic.
Mm-hmm.
That is, I think, I may be wrong, but is it deterministic? Let us verify. Is the output
You
of the hidden functions.
is the output you removed is.
Yeah, wait, deterministic.
Sometimes yes, sometimes no. Clean way to think about it. Input latent, output latent.
Okay, yeah, non-deterministic for this scenario. So for this, what about for latent frames? For latent frames and Cosmos prediction models. Okay, so it says that the model prediction part and Cosmos prediction model are deterministic. Given the scene and the structure, predict the next latent. So it says that it's not mostly guessing, it's more of computation, that what would come next.
Yeah, it's like probabilistic.
Yeah,
Then it becomes stochastic.
yeah, like when we move it to, I think, wait, where are we moving it to? Hmm. Wait, it says that, hold on, where the hell is it? Wait, I'm confused now. Cosmos production strip, latent frames. Yes, so the generation process is stochastic. Right. Okay, okay.
Wait, number of latent frames model configure parameter state T is reduced to 16 from default 24 because
Uh,
let
wait,
me
let
put
me
a-
just change the browser. This is a shitty browser. Calling the one and only Comet. It's time for Comet. Again, need credits. Sponsors awaiting. Okay, are you able to see the screen?
not yet.
Mm, I'll make sure to fix the stream as well.
Oh, okay. Now I see. Okay. Let me check the stream. No viewers today. No, zero viewers.
Puta.
But we are at 50 subscribers somehow.
Okay, so
Hmm. Wait, can you scroll up a little
okay,
bit?
okay, dude. Half of the time you're saying either to scroll up or to scroll down.
Bro,
What the
but
hell
you're
is reading?
scrolling. I
Dude,
was
what the
reading on
fuck?
left,
We were over
bro.
here. Okay, we were over
Yeah,
here.
yeah, yeah. I was
Now
reading
you're
on the
saying to
left.
scroll up. What the fuck?
Bro, in the fucking perplexity window, I'm saying.
Okay.
Mm, okay, scroll down in that window. Wh- Okay, so what's the exact function, like latent frames? Okay, data set. Mm-hmm. Yeah, we can go down. Num frames is set to 61 to match. Then this sensor. And okay, summarize those 61 frames into only 16 latent time. What? Can you scroll down a little bit? 16 latent time steps internally. Oh, okay. Okay, so okay, we can go down. But yeah, okay, what's the difference between num frames and state T over here?
Number of frames that we are taking
And
in the
state T?
loader. So state T is the number of uh, clips that we are taking. Remember when we're training the RoboFact data, we have
Uh-huh.
to play with the frames that the number of time frames that that model is taking at once, or trying to learn or go trying to go through the frames to understand what what does the video is trying to capture, right? So if you have a larger number of frames, let's say if you have 24 range, then you can capture a lot of changes in that video that is happening, right? But if you have a smaller set of frames, then you won't be able to capture a lot of motion. Since this we have over here, it says low temporal variability, right? Which means that there has been not that much state changes, because it says that we can safely drop state t from 24 to 16 because we don't need need to model rich fast changing motion. Why? Because we have this
Wait. What did you say? Can you repeat that?
where is it, we can safely drop state t from 24 to 16
Yeah. I
because
understood that it's that the content is not that rich because there is like not a lot of variability in like soil
yes,
and all
yes,
that stuff.
yes,
Yeah.
yeah.
But then
Yes.
what? But what is state T?
Number of frames that we are taking, number of frames, latent frames that we are taking in the model. State T is the latent frames. State
Oh,
T
okay.
is latent frames,
Oh,
number of
okay.
frames that you are taking in the model.
Okay. So number of num. So over here num
I think,
underscore
wait,
frames.
explain it to a 5-year-old.
uh, From moment plant and dirt basically stay in the same place. The leaves don't suddenly okay, scroll down. Okay. So num underscore frames equal to 60 is like the total frames, and state T is the latent frames that we are selecting out of those 60 to use in the data set because we
Yeah.
can use, right?
Yes.
Okay. You can scroll down now. We can keep on reading. Yeah. Yeah, this was the dataset schema. We read this. And you can expand that doc window a little bit.
Which window?
Document window, yeah. Yeah, let's go down. Yeah, down. Caption generation. Captions are generated using a template populated with metadata from data capture pipeline, crop type, blah blah blah, and augmented with a VLM of for natural language description whether data can be appended when available. What the fuck does that mean?
Hmm.
Oh, this is like the text prompt for each video.
Yeah.
They have metadata from robot logs, what crop it is, okay, which way the camera is pointing, what the feed looks like. They plug into those captions template like okay, scroll down. No, in the perplexity window. They have metadata from robot logs. Okay. And what model are they using? Cosmos Reason, right?
Yeah,
Or
they're
Cosmos?
using Cosmos Reason, but to generate the text, they're using Gemini 2.5 Flash for natural language description.
Okay. They plug those into caption template like filling blanks in sentence. LM looks at the frames, add more natural detail. Okay, one sec. Hmm. Okay. Oh fuck, bro. This is so exhausting.
Dude, if you're doing all night, right, it's gonna be exhausting. Why do you want to make things unnecessarily tough?
No, I'm not trying to make it
No,
tough. I just
yeah,
want
you're
to
trying to make it
push.
definitely, dude.
I'm just trying
If
to
you
push, bro. Push like.
dude, it's not pushing, dude. This is something that you do unnecessarily tough, right? Like
Bro.
this thing can be done in the morning as well. No, but you want to work your ass off, and then you want to again work your ass off. So this is unnecessary pushing,
Bro,
right?
wait.
Clear, bro. Clear.
Listen,
This is
listen.
no. This is unnecessary waste of your time for at this point, right? If
No.
if you're saying that you're exhausted, right, at 3 a.m., then for sure you're definitely exhausted. You are just forcing yourself at this point.
Okay, let's wait. We can do one thing. We can just finish this document and then we can end the stream.
Yeah. Okay.
Because I think this document will help us to conduct our
Right.
next
That's what I
experiment.
said. That dude, I went through the whole thing when we were having discussion, right? So I went through the whole thing. That's why I did not move from this post because this was really interesting because this was something that we had already tried to do and we
Hmm.
failed. But
But we didn't run it against Cosmos, right? We ran it
yeah,
against
because
that stupid Quen.
because what we did was we were trying to do how would I say, we were trying to do vibe vibe experimenting.
Hmm.
I would just say vibe experimenting, and then it gave us some lead that okay, it's our normal vision language model are not that much capable of analyzing the depths of images as
Hmm.
compared to the Cosmos models. I think as of now we haven't tested the Cosmos models yet, but
Yeah.
we can definitely test those. Um, but yeah, let's first focus on this. Okay, so I
Hmm.
think what they're trying to use is they're trying to use Gemini 2.5 Flash for the natural language
And I think
description
it's like an
generation. Right over
outdated
here,
thing.
we have a caption as well, right? We have the caption for the example output, and then the template. Okay, this is the camera angle view from an agriculture robot, and something like
Hmm.
that. So this is how they are doing. So this is the most important part, the post-training configuration, the control modality. So this is what I was talking about earlier. while I was going through when the screen was blurred. Okay, let's go through this. Both depth and edge control modalities were evaluated for this domain. The depth control produced significant better results, and edge control post training showed only slight improvement. Effect on the edge maps: strong direct sunlight, shadow boundaries creates furious edges. No effect. Depth is illumination invariant. Auto exposure variation cause frame to frame edge. No effect. Huh. Recommendation for any outdoor physical AI domain with uncontrolled lighting, depth is the preferred control modality over the edge. What is modality over here? What do we have? Control versus depth. Wait, control versus sorry, depth versus edge control. Okay. Oh, I see. I see. So right now, in the post training, what they're saying that they're either training on depth or edge. So depth is the variance that you are getting when we are mapping out the images based on depth. But as we compare it with edge, so it's like, okay, you are trying to draw the lines and look for the changes in the lines.
Mm-hmm.
Right. So, for example, let's say if we look at this image, this would be a perfect example right now, I think. So, this image, right? Uh,
Mm-hmm.
the first image that we had showed us the lines, right? So, this lines over here in the leaves. If we can see the changes in the lines, then we can do edge control, right? But when we can see the shadow or the depth, then predict the output based on the change in the depths we are having, or change in the lines, or change in the spatial geometry that is happening. So those are the modalities that we can control, I guess. In where is it? Post training configuration, right? So overcast, diffuse light. Okay, I think the overcast diffuse light would be this example over here. Wait, it's gonna pop up. One, two, three. This one,
Okay.
right? The third one that showed some shadow, right? So that
Mm-hmm.
would be the overcast diffused one, I'm guessing.
Okay.
And
Strong direct sunlight, auto exposure variation, overcast diffuse light. Okay. Effect on depth, no effect, no effect, no effect. Causes
and then
frame
we
to
have
frame edge
specular highlights, such as wet
false
leaves.
positive edges.
Right, strong direct sunlight, right? So this could
Mm-hmm.
be we have a lot of so this is like shadow thing, and then this is like normal modality over here. But
Mm-hmm.
some of the examples, okay, this is wet leaves or disturbed leaves
Mm-hmm.
in that manner. And we also have like strong sunlight. So those are the things that they have, I think, looked for in the conditions. So effect on edge maps, effect on depth maps. So as we discussed, what are edge and what are depth modalities? So shadow boundaries creates furious edges, whereas effect on the depth map, no effect. Depth is illumination invariant.
Mm-hmm.
Auto exposure causes free frame to frame edge consistency. I don't know.
The explanation is rooted in outdoor agricultural lighting conditions.
Okay, for any outdoor physical AI domain, the with uncontrolled lighting, depth is the preferred control modality over edge. That is the recommendation. Depth control. Okay, this is how we can control the depth. That's what they are saying. Okay, number of frames. Mm-hmm. So these rows are explaining why edge maps break under outdoor lighting, but depth maps don't care. So strong direct sunlight. The sun creates sharp shadows at the leaf, row, and boundaries. An edge detector sees those shadow boundaries as strong intensity changes, so it marks them as edges that aren't real objects. Huh.
Whoa,
I
what?
see.
Wait. These rules are explaining why edge map break under outdoor lighting, but depth maps don't care.
So, like as we discussed that, like in the if we see an image with shadow, right over here, it says that an edge detector sees those shadow boundaries as strong intensity changes. So I think it is marking that okay, there are some more plants or something, or they're having more leaves because those leaves are creating some shadows, and those shadows are being considered as edges from from the Cosmos model when the edge modality is selected. I would say. Are you
Okay,
getting that? Are you getting that?
okay.
What I'm saying?
Can you repeat your last point?
So I'm saying that. So if you take a look at this image right now
Yeah,
that went away.
yeah,
So when sunlight is dropped upon the leaf,
yeah,
so it creates a shadow,
yeah,
right?
yeah,
Now you have the shadow.
yeah.
So when you have the shadow and you use edge modality,
Mm-hmm.
right? So what
It gets
edge
fucked up.
yeah, it gets fucked up. Why? Because edge modality thinks that there has been some change in lines or
Mm-hmm.
boundaries. Like
Yeah, yeah, yeah.
these shadow boundaries, it is seeing
Got you. Yeah,
as
yeah, yeah.
strong intensity
Mm-hmm.
changes, and it fucks up the
However,
image.
depth only has a distance. The geometry
Right.
doesn't change when the sun moved, so the depth map stays the same. No effect. Depth is illumination invariant. Okay, correct.
Right. And
And
then
then auto exposure variation, camera auto exposure pumps brightness up and down as lighting changes. That that changes contrast between frames, so edges appear stronger, weaker, or disappear. Edge map flicker frame to frame. Okay. Depth values don't depend on brightness, so depth maps remain. Can you show me that table one more time in the document? Okay. No, this is
no,
too. Yeah. Yeah,
no,
this
this
one.
one.
Oh, okay. Yeah. Yes. Okay, I got it. Recommendation for any outdoor physical AI domain with uncontrolled lighting. Depth is preferred control modality over edge. Got it. Yeah, we can go down. Let's see the code a little bit.
Code is like nothing
Oh,
much.
normal. Okay.
It's experiment. You have a dictionary. You have a data loader.
Yeah, got it.
With
Another
like
dictionary.
the basic machine learning PyTorch training modality that you would go with.
Okay.
So
Key
these are the key
hyperparameters.
hyperparameters. I think the control type, that is a depth that that I think we know why we should go
Uh-huh.
with.
Yes.
and
Training
then and
iteration
then
is
and then training
4,000.
iterations that are like 4,000
Early but
training
quality
400.
continues improving. Train longer. Okay. Resolution is 480p. Rate in frames Vino 16. Depth guidance scale is point 0.8 inference. Strong structural adherence with room for surface detail. Point 0.8 is like the one that they use for this project, right? But
Yeah.
it can depend for like different projects, it can change.
Yeah, I think yeah, it would like definitely differ from project to project, or no, it wouldn't differ to project to project. It would differ on what kind of, I think, image we are dealing with, or what kind of data set are we dealing with. Let's say if we might have some images or video frames of plain surface that would have a constant depth, then at that point we don't need that depth guidance
Hmm.
in that manner.
Okay.
And training
Training
inside
insights.
training for longer improves generation quality in a way more visible in output sample than in loss metric. Recommend visual inspection of generated outputs at checkpoints rather than stopping at loss plateau.
Okay. Launch training. Go down. Launch training is number of GPUs 8. Okay. Data directory. Fuck it. Blah blah blah. Okay. Config. Okay. They're using Cosmos Transfer too.
What? Yeah, that's what I said. They're using Cosmos Transfer too.
Okay. Convert checkpoint, training convert, DCP format, PyTorch for inference, go down. What does that code do? One second. Go up. Use checkpoint EMA blah 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 for all inference
It's for
runs.
loading the model checkpoint, like weights, weights of the model.
What like in Cosmos?
Yeah, dude, you have to load your model weights, right? Checkpoints or training weights that you have created.
I don't
You
know
can
how to
either
do
load,
that.
and this is how you do it.
Okay.
Like
But
you
like,
go,
okay,
you
what are the values? Like, what are the weights exactly?
this is the weight format, dude. Float 16.
Oh, okay.
It's gonna be in matrix format, right? Like those
Yeah.
computed sums. Like so, it's
Okay.
wait. Do you know back propagation?
Yes.
Right, you remember back propagation,
Yeah,
how
yeah,
you
yeah.
can do back propagation relative to a certain variable or a
Yeah.
certain parameter, and then you
Uh-huh.
can fine tune it, right? So you do
Mm-hmm.
that whenever you train your model, and then you just store that state. So whatever the parameters that you have tweaked, and you whatever the best position that you have found for your models or neurons, that okay, this is the weight or this is the value that you have to go with to perform the best, you save it and create a snapshot of it. And
Mm-hmm.
whenever you have any other model or something, then you can just put those weights or those values as variable into those back propagation values, and then it's gonna generate those.
Mm-hmm. Okay.
I
Got it.
think, do you got it, or
Can you put it in perplexity and just get it to show an example of this?
oh wait.
What happened?
It ran right. Checkpoint a saved copy of model weight. These weights are exponential moving average of the training weights, which are usually smoother and give you better, more stable generation with raw.
Exponential moving average of the training weights.
Yes. So that would be the proper technical term, EMA. Checkpoint EMA, exponential moving average.
Mm-hmm.
B float is the precision like float 16. Since we have good hardware, we are going with more bigger integer values, 16 bit. If let's say we have a smaller hardware such as our MacBook, then we will do maybe 8-bit
Mm-hmm.
precision or 4-bit, because we don't have that much GPU power to train the same model on,
Mm-hmm.
right? Mhm. So when you generate images, videos, and inference, always load this EMA checkpoint, not some other intermediate or F32 training checkpoint. This is
Mm-hmm.
recommended for stable version of for deployment. So this is what
Mm-hmm.
it means, that okay, when once you have trained this model and you need to make sure that everything runs fine, you have to
Mm-hmm.
save it in a checkpoint state, and then you can use it for further inferencing or further training or refinement
Mm-hmm.
as needed.
Mm-hmm. Inference generating synthetic images. Add inference time, construct prompts describing the target scene, crop type, growth, stage, field conditions, lighting, and optionally disease symptoms. From precision matters. Specific descriptions of visual. Okay, so I think this is the part where we could be, better off. Like, do you understand? Like, this is like the prompt that we're gonna put in Cosmos when it's gonna inspect a warehouse robots for their failure.
Wait. Generating synthetic image at inference time, construct prompts describing the target scene, crop type, growth, stage, field condition, light, and disease symptom from precision specific. Hmm.
Description of visual features produce better results rather than vague ones. Depth guidance scale use zero point 0.8. This provides strong structural adherence to depth control signal while leaving freedom for realistic surface detail and lighting. Depth distribution matching inference time maps must use the same normalization as training. What does that mean? Deep distribution. Yeah, can you copy this?
Which one?
Depth distribution mapping.
Oh, I see. Same normalization values. I know what it does mean.
They take raw depth and run some normalization pipeline. Example clamp scale, maybe invert map to 0255. That reduces certain distribution of values, how many pixels are near versus far, what the histogram looks like, etc. Inference one time maps.
Do you know what normalization means?
Yeah, normalization, I know. Let me.
If at inference you process depth differently, example, different scaling, invert, near, far change, then model sees a different depth distribution than it saw during training and generate quality drops. So depth distribution matching. When you do inference, apply the same exact depth pre-processing noise you did for training. You got it? Did you understood?
Explain it to me like a 10-year-old.
Arey, dude. Let's assume that you went shopping. No, you are a well digger or a well searcher, right?
Okay. Hmm.
And you are looking for different kind of wells,
Okay.
right? So in
Hmm.
training, you used a measurement tool to map out the values, right? Let's say the depth of the wells that you are looking at were 100
Mm-hmm.
feet or 10 or more than that, right? Now you have to normalize those values in a way so that it becomes easy for your model or your for to understand, right?
Hmm.
So the same normalization method that you used in your training, you have to use the same normalization procedure in your inference as well. It means that whatever values that you whatever depth values that you are generating should follow the same normalization that they have followed in inference. So, for example, you have a video of a crop, let's say, right? And in training, that you did something, you normalize the depth in a way, and when you give the model for inferencing the data, right?
Mm-hmm.
You have to provide the same depth in the same normalized manner, otherwise the model won't be able to predict properly.
Okay.
You got it?
Yep.
Okay,
So during
so
training, they take yes, produce or distribution values. How many pixels? Near versus far, war history.
example, healthy soybean rows, bright sunlight, an angle
Mm-hmm.
view of soybean plants growing in row on farms. So I think as they have said, so for this text generation they have used Gemini,
Mm-hmm.
and for this image generation they have used Cosmos.
Okay, but what's the point of generating both the text and the synthetic data for this? Like, how are they
So
getting
it's a label,
combined?
right? It's a label, right? You have to label what you have to
Yeah.
label in a way that okay, what did model understood? That would be the important question, right? Because since we are dealing with latent states and latent frames,
Mm-hmm.
so when you say generate or when you give a prompt to a model, healthy soybean rows and bright sunlight, so we
Mm-hmm.
need to make sure that okay, what the model is trying to understand, I think. So that's why we need to give out a caption, and it will help us to, create some kind of uh, data labeling as we
Mm-hmm.
grow.
Okay.
That okay, this is what robot is doing, this is what robot should do, this is what robot should not do.
Mm-hmm.
Those kind of scenarios. For example, like over here, we can say that this is like over here disease soybean. So this is like maybe creating synthetic training data for the bots that okay, this is how a disease training looks like,
Mm-hmm.
right? So those things can be used.
Okay. Got it. Scroll down.
That's it.
Result is generation quality base. Okay. Okay. So what should our next experiment look like for this Cosmos reason?
We can replicate this experiment, or maybe just take some other database.
Yeah,
Start.
we need to take some robotics database, right?
Yes, so we are gonna do that. I think to create a photorealistic image data. So we image data or something.
Mm-hmm.
So yeah, that we can keep that as our next stream project that we will be implementing what we have learned today.
Okay. Yeah, bro. I'm out of memory.
Yeah, I know. I can I can hear it in your voice.
Mm-hmm.
Okay then.
But
It
we
was
are
fun, guys.
pushing. We are pushing.
Yes. Progress is there. We are keep pushing, and calling out all the sponsors as
Yeah, with all the
we need
two
tokens.
viewers,
We need tokens. We are only asking for AI subscription. That's all. We
AI
and
subscriptions, and
compute
funding,
and compute.
compute, and funding for equity. We are ready to give up 2% of our
Day by day,
company.
dude, the day by day your dilution is getting bigger. Initially, it was one. I think by end of this month, we would have diluted 25%.
Dilution. I think it's time to pull in the major angel investor.
Yes, one and only again, JP Morgan,
JP Morgan, nah, the king.
Dubai, JP Morgan, Dubai.
Jamie Diamond's other hand, right?
Uh,
The Jamie
yes,
Diamond's right hand.
yes. A big infusion would be over here. Liquidity infusion. Money will be printed. Money will be printed.
The biggest VC deal
VC.
of the century.
Balle Venture Capital.
BBC.
BVC. Big Balle
BBVC.
BBVC. Yes.
Big Balle Venture
Big
Capital.
Balle Venture Capitals.
Bro, you know what we should do? We should run a Ponzi scheme. We should ask
Bro, uh,
our BBVC to open like a shell company which should take some loans from
bro,
banks,
BBVC don't do those kind of things.
and then they will fund us, and then stuff will
For
happen.
for sure.
Ponzi schemes. Okay. So, okay, let's just define what our next experiment should be. Like, just in the pipeline, how are we going to integrate this? First of all, we need to come up with our failure, like coverage gap analysis, right? So,
Mm-hmm.
after watching like all the failures videos of the robots,
Mm-hmm.
we need to generate a coverage gap analysis. And I think Cosmos is going to help us do that.
Mm-hmm.
But we are going to use our own infrastructure, like our
Mm-hmm.
own set of promptings and way of running Cosmos on those models, on those
Mm-hmm.
data sets, sorry, to
Mm-hmm.
generate that coverage gap analysis.
Mm-hmm.
I think that should be
I
the
see.
next experiment.
I think I would primarily focus on getting the data set and then
Correct data set, right?
correct data set with like because like we have seen that Cosmos works with the different kind of modalities and we have to make sure that we are choosing the right modality to understand our model is able to predict accurately with less training, right?
Mm-hmm.
Because since in this experiment we also did learn that you
Mm-hmm.
cannot just choose any modality for your post training configurations, because if you go with the wrong modality then there is a higher chance that you will either overfit or underfit and you won't
Mm-hmm.
be able to get accurate predictions.
Yeah, got it. I think it's exactly 3 a.m. and I think we should end the stream now.